Okay, let's talk about collision theory and the rate of different reactions. Now, first of all, in order for molecules to react together, they need to collide with each other, obviously, and they have to have enough energy to make the reaction happen. Throughout the unit, we're going to call that the activation energy, capital E subscript A. And they have to collide at the proper angle. Some teachers will call that with the appropriate geometry. If you know anything about organic chemistry, you'll recognize this as a carboxylic acid. Now this is the acidic hydrogen on that molecule. So the question I have for you is that if you have a molecule of base somewhere in this solution, and that molecule of base collides over here at that end of the molecule, will it react? The answer is obviously no, it will not. That's not where the acidic portion of the molecule is. If the OH attacked over here and collided from this angle, the answer is yes, it would have reacted. That should be enough proof, or at least of an idea, to prove to you that geometry is important. There are some complex geometries that can happen between different molecules. All you really need to understand in early years is geometry can affect it, and not all collisions, even if they have enough energy, will result in reaction because it has to hit in the sweet spot of the molecule. Okay, so it stands to reason that we can increase the rate of reaction by making more collisions happen, or by increasing the energy with which each collision happens. Now, that means we can increase the reaction rate by increasing a whole bunch of other things like temperature. Temperature will make the molecules move faster. In fact, kinetic energy, EK, is proportional to the temperature in Kelvin. Double the Kelvin temperature and you're going to double the average kinetic energy of each molecule. So they have more energy, each molecule, and the molecules are moving faster for that reason. Because they're moving faster, temperature increases the number of collisions that happen within your sample. And because each molecule has more energy than it did before, each collision is going to be, on a relative basis, more effective than they were at a lower temperature. You have a higher percent chance that the molecules colliding have enough energy to get over the activation energy barrier. Temperature is the only thing I've listed here that affects the rate of reaction in two different ways: number of collisions and percent effectiveness. Now, pressure, that's increasing the number of molecules per liter of gas. Concentration, increasing the number of molecules per liter in an aqueous solution. And increasing the surface area, or decreasing the particle size for solids, all help to increase reaction rate in a different way. Because you have more molecules per unit of volume here, and because you have increased surface area, if you powderize a solid, you're simply going to increase the number of collisions that happen. Each collision will have the same chance of happening because only temperature can increase the kinetic energy of the molecules. So maybe, 50% of the collisions that you have in a certain sample are effective. Well, you can still make more of the reactant molecules react if more collisions happen. And we do that by increasing pressure, concentration, and surface area. Now, a catalyst affects the reaction by decreasing the activation energy barrier over which it has to get over. Now, if you have something like A plus B becoming D, and that has a very high activation energy barrier, and then the addition of a catalyst will lower it, you can't even really say that there's more collisions happening or the percent effectiveness of each collision is happening, but I'm going to put my check mark there anyways, because more of the reactant molecules will be able to traverse the activation energy barrier simply because it's a lower barrier because it's taking an alternate pathway. Okay? Now, something that other teachers include is nature of reactants. This is just another way to say lithium reacts differently from gold, and fluorine reacts differently from iodine and hydrogen. Those are very obvious things, and it affects how high the activation energy barrier is in the first place. It doesn't really affect the number of collisions or the effectiveness of each collision. A different reaction has a different rate, and you're going to have to accept it. Cool? Cool. Let's talk about